discussing the frequency response of an integrator. The basic integrating circuit, integrating amplifier using operation amplifier we have already discussed, and it was this. This is the input signal Vi and resistance R1, capacitor Cf, and of course these power supply is there. This is load resistor across which we take the output, and this is to reduce the offset effects. About offset effects we will definitely talk. So, this is around R1, and we have seen that the output of this is minus 1 by R1 Cf integration Vi dt, where Vi is the input signal. And if we take that input signal Vi is expressed as A0 sin omega t, then the output is, then the output of the integrator is V0 minus 1 by R1 Cf and integration A0 sin omega t dt, and this gives V0 equal to A0 omega R1 Cf cos omega t. This is if we take as first and this is the second, then we can write the ratio of the two for the peak voltages, taking peak voltages both at the input and output. The ratio, which is gain V0 by Vi, its magnitude is A0 by A0 omega R1 Cf, and so it is equal to 1 by omega R1 Cf, and this is gain of the integrator. So, what we are seeing, that the gain is frequency dependent. As the frequencies, this angular frequency is omega, which is 2 pi f. So, as the frequency f increases, the gain falls. So, gain is proportional to 1 by omega the frequency, and the plot for this is this is the frequency f1 at which the gain falls to 0. This is gain in dV, and this value, this represents V0 by Vi, this magnitude of this quantity. Now, the gain is falling, and it can be shown that this fall is minus 20 dB per decade change in frequency. So, if frequency becomes 10 times, then gain becomes 1/10, that is the meaning, and the gain falls. And here the f1, this frequency, this is frequency, f1 is given by 1 by 2 pi R1 CF. This we can get from here actually. This is gain, and when at the frequency at which gain falls to 0 is given by this. And so this is the frequency response of the basic integrator, this integrator circuit. And now we have discussed that there is a problem with this circuit, and the problem arises because of the offset currents and voltages, and the capacitor gets charged, and it is amplified, and there is a output even when there is no input. And these problems can be tackled by attaching a resistor along with the capacitors in shunt. So, now we discuss the frequency response of a practical integrator. Frequency response of practical integrator. So, the circuit which we are considering is now this. This is RF, the resistance we have included, and this is CF, and this is connected here, and this is load across which we take the output, and here we connect the input. So, this is the practical integrator. Now, remember the basic, that true integration occurs when the impedance of this combination of CF and RF is capacitive, and this will be capacitive only when the effect of this capacitance dominates. So, and we know that at low frequencies, the parallel combination of the reactance of this capacitance in parallel with RF at low frequency, this will be very high impedance, reactive impedance of the capacitance will be very high, and this parallel combination will give the effective value as RF. So, that means at low frequencies this inclusion of this resistance RF, this limits the lower frequency for integration. That means at very low frequencies where this condition is satisfied, the output will not be the true integration of the input. And then, so for true integration, this reactance should be very small as compared to RF. That means 1 by 2 pi f CF, this should be very small as compared to RF. And we can define a critical frequency beyond which integration will be all right. So, we define a critical frequency Fc we define a critical frequency Fc such that Xc is equal to Rf, and substituting the value of this 1 by 2 pi Fc now into Cf, this is equal to Rf, or the frequency Fc is equal to, from here, 1 by 2 pi Rf Cf. This is the critical frequency, and this will give Fc give a break frequency, gives break frequency in the response. And the response is this. This is frequency, this frequency is F1, and this is at this is the 20 dB per decade fall curve, and here this is the 3 dB line, and this gives Fc, this cutoff frequency which we have written, this Fc, this is this value, and for this F1 we have written earlier, F1 is equal to where gain falls to 0 dB, this is gain in dB, and this is Rf by R1 gain. So, and this gain is, this frequency is 1 by 2 pi R1 Cf. There is a difference in two break frequencies. F1, this is because this resistance will be smaller than the resistance which is used with the capacitor. So, this contains the first resistance, here this is Rf, and Rf is definitely higher at least 10 times, normally 10 times of this. So, this is the frequency response of, this is the frequency response of practical integrator. And what we see, that below Fc frequency, which we can calculate from this expression, below Fc true integration will not occur. So, true integration in the frequency limit, in the frequency or between the frequency Fc and F1. So, actually F1 is chosen quite high as compared to Fc. Fc we choose very high as compared to F1, and it is a thumb rule that Fc is 1/10 of F1, and in that case Rf will be 10 times of R1. This resistance is 10 times of this resistance in the design. So, that is this, and integration will occur in this frequency region. The integrator is not used below the frequencies Fc. About the applications, Applications of the integrator, these are used in analog computation, and in wave shaping circuits. And of course, there are similar other uses. So, this was about the integrator or integrating amplifier using op amp. Next, we take a differentiator. That is the next thing which we are considering, the differentiator. In differentiator circuit, the output is proportional to the rate of change of the input at that instant. I repeat that output in the differentiator is proportional to the rate of change of the input, and rate of change is as we will see, that means what I am saying is this, is proportional to, when input signal is V I, then output is proportional to this, and this circuit is called differentiator or differentiating amplifier. And this can be again realized in inverting amplifier. Inverting amplifier, the capacitor R1, the resistor R1 is replaced by the capacitance, then the circuit works as a differentiator. So, if the resistance R1 of inverting amplifier is replaced by the capacitor, then this is the circuit. This is RF, this is C1, and here this is VI. The resistance which is equal to roughly RF, and here is the load resistor across which we take the output. This is the basic differentiator. Basic, and of course, these power supplies are there, which are not essential to be shown because it is implied that they are there. No electronic, repeatedly I am saying, no electronic circuit will function unless the transistors of this in the device are properly biased, and for biasing we need the DC supply. So, these are two supplies here. This is the charging current IC which the signal will send, Vi will send, and here is current IF. This is IF. This is the small current IB, and IB, this repeatedly is being said that IB, because the input impedance is very high of the device, it is in 1 or 2 megohms. So, IB can be taken as 0. If IB is taken 0, that means no current is going in this arm in the inverting input, then we can write IC equal to IF, IC equal to IF. And how much is IF? IF, this current, 2 voltages, this is V2 this is V0. So, V2 minus V0 by RF, this is this, but we know that V2, the inverting input, is at virtual ground potential. So, since V2 is 0, virtual ground, everywhere we are seeing the advantages in inverting amplifier, the advantages of virtual ground, because the concept of virtual ground makes the analysis much simpler. So, this is virtual ground. Then IF is equal to minus V0 by RF. This is one expression, and how much is IC, the charging current. Charging current we can write IC, this is equal to the capacitance into, from simple capacitors theory, and voltage difference. So, Vi minus V0 by dt, and sorry, the two voltages, this is at Vi and this is at V2. So, this is 2 V2, which is 0, but V2 is 0, and hence IC equal to C1 dVi dt, and because the two currents are identical here, IC is equal to IF. So, these two expressions we have already got for IF, and here this is for IC, and so we can write therefore C1 dVi by dt, this is equal to minus V0 by RF, or V0 is equal to minus RF C1 dVi by dt. This is what we said in the beginning, that this is all constant, and this sign inversion is it does not make a difference. This also we have been talking, and so the output is proportional to the rate of change of input. So, let us take two cases when input is a sine wave. Input is a sine wave, output will appear as cosine. At the output we will have cosine function, cosine wave, and for triangular input, a triangular input will produce a square wave output. Will produce square wave output. Now, we talk about again, because for these integrators and differentiators, frequency response is very important. When the input frequency, the frequency of the input signal is changing, then how the output will vary, that is of significance. Now, here we should note in this basic circuit of differentiator, there are two problems. One is that gain of the amplifier is RF by XC, where X is the this is, for the inverting amplifier the gain used to be RF by R1. R1 was the resistance here. Now here it is a capacitance, so the resistance will be replaced by the reactance, and this reactance will go low very fast at higher frequencies, because this is Xc is 1 by j omega c. So at low frequencies this is at high frequencies this is very low, and therefore gain rises with frequency at the rate of 20 dB per decade of frequency. That means when frequency becomes 10 times, then it changes 10 times, so 20 dB. So this is the change, and at very high frequencies this will be very low and gain will become very large. At very high frequencies gain is extremely large, and that makes the circuit unstable. That makes the circuit unstable, and that way the frequencies noise, they will also may get amplified. Now because of this there is a high frequency noise which will be heavily amplified, and that will dominate the differential output. So it will not be a accurate differentiation at very high frequencies. So to take care of this fact that gain becomes exceedingly high when the frequencies are very high, we attach a small value resistor and we get a practical differentiator. Practical differentiator is this. This is RF, this is the resistance R1 which we have attached, and R1 is quite small as compared to RF, and this is C1, and here we attach the input signal. this resistance is equal to Rf, and these are the supplies. This is a practical differentiator. Practical differentiator. And here now at very low frequencies, frequency of the signal tending towards infinity, at very high frequencies, at very high frequencies, here the gain was rising very fast with the fall in Xc. In this case, now when this is almost is a short, then gain will be restricted to this, and this normally may be 10, 12, 15. So, gain will be this at very high frequencies, and the frequency response of this practical differentiator is this, and here this was the gain going up very fast with frequency. This is frequency, and this is in dB. Now here for the practical one, the gain will stay at very high frequencies when this capacitor is almost acts as a short. At those frequencies, the gain will be this here. This is Rf by R1. So this is the response of a practical differentiator. This is practical differentiator. This was for the ideal one. This is for the basic, which we have showed, the integrator, basic integrator, and this is the practical integrator. And here this frequency is F2 or Fc, we can say, and this is F1. F1 is the frequency where the gain will fall to 0, and F1 will be given by F1 is 1 by 2 pi Rf C1 at the frequency at which this becomes the gain becomes 0. So this is the frequency, and the inclusion of R1 that has restricted, that limits the high frequency range of the differentiator, and this Fc will be given by Fc is given by 2 pi R1 C1. So again, as in differentiator, we have two frequencies, F2 which is same as Fc, which I have written here. This we can write F2 or Fc. This is this frequency, and this is the difference is of R1 and Rf. So beyond this frequency F2, no good differentiation, no true differentiation of the input will appear, and so differentiation is there in the frequency. True differentiation occurs in the frequency range F1 to Fc or F2, whatever you write, and this frequency is set, Fc is set quite high in comparison to F1, so that there is a good range of frequencies over which true differentiation will be possible. About applications, this is we have discussed. So, the basic circuit is not used for differentiator, but this circuit is used by inclusion of resistance R 1, and this is the frequency response of the practical differentiator. The inclusion of R 1 puts a limit on the high frequency, that means it saves the circuit from instability of very high gain, and so a true differentiation occurs between the range f 1 and f c. And about the applications of differentiator, they are the same as the integrator, that they are used in analog computation and wave shaping. So, this is all about the differentiator. So, we have taken several applications, we continue with few more, and that will show the versatility of the operational amplifier. So, after these summing circuits and differentiator, integrator, sign changer, and we now go for another class of applications, and these are active filters. Active filters. First thing is, what is a filter? Filter is a frequency selective circuit. Frequency selective, that means you have a spectrum of frequencies and you want to select for your system, that your system should respond to certain frequencies. So, how to get them? Frequency selection can be done by using filters, filter circuits. Now, there are two types of filters, passive filters and active filters, right. Filters, these are frequency selective circuits, and they can be two types, passive filters and active filters. Passive filters and active filters. Now, passive filters can be realized, frequency selection circuits you can make by using capacitors, resistors and inductors. You must have done, you have done a resonance circuit. What is a resonance circuit? Resonance circuit is a frequency selective circuit, and resonance can be obtained by the combination of capacitor resistance and inductors. But these filters, the passive, these are called passive filters, they are inefficient. Inefficient in the sense, there are 2 points. One is that these components will dissipate certain signal. So, signal is attenuated in passive filters, number 1. Second thing is that frequency response of passive filters is not as good as in the case of active filters. So, active filters are the ones which make use of a active device, transistors or op amps, to make filters. Operational amplifiers are very widely used. In fact, they have replaced BJT and all other uh, circuits for making active filters, because handling of operational amplifiers is not at all difficult, plus they are not expensive, and hence active filters make use of operational amplifiers, and these circuits are very widely used. Now, there are four types of filters, four types. Four types of filters. What are these types? First I name them and then I will elaborate them. One is low pass filter. Low pass filter. Then we have high pass filter. We have band pass filter. And then finally we have band stop. Band stop or band reject filter, or band reject filter. These are the four different kinds of filters depending on the selection of frequencies for the working of the circuit, that which frequencies we want to choose. And in signal processing, this filtering of frequencies is a very important process. And so, we now first talk about these filters. The low pass filter. First we take low pass filter. Low pass filter is the one which is supposed to pass. By pass we mean that they will go in the circuit for further processing. So, certain frequencies from very low to a certain high frequency, they will be allowed to propagate. Beyond that frequency, signals will attenuate heavily, very heavily, and they will be prohibited from going for further processing. So, that will be low pass filter. A ideal, first I take ideal low pass filter, then the actual low pass filter, practical. So, this is the case. This is gain and this is frequency. This is the pass band, this is frequency. So, this is pass band and all this is stop band. And let us call this frequency as FH, and this is ideal. So, what is the low pass filter? From 0 frequency to up to a maximum of say FH frequency, it will pass. That means, signal will pass through the circuit without attenuation, and it will be, it has been selected in this frequency range, it will be selected and it will be further processed. And in ideal, this is the case of ideal filter, in which gain in the attenuation in the pass band attenuation in the pass band in a ideal filter is 0 dB, that means no attenuation, while attenuation in the stop band is infinity, infinitely high attenuation. So, this is for ideal filter. Now, electronically we cannot have this ideal gain frequency response, because there is no process by which this break can be that sharp. So, the practically what we have is this. Here we have this frequency is FH, and so here this gain, this is 3 dB fall, and this is frequency. So, this is the case that gain will start falling here and then it will go and fall very fast here, and up to this frequency 3 dB fall will be corresponding very close to HF. Here the fall will start and 3 dB has fallen by this frequency, cutoff frequency, and beyond that again in the ideal case it was infinite attenuation. Here the loss, the attenuation will be high, but it continues for certain frequency region. So, this is the response, and we will drive an expression for this cutoff, what is the highest cutoff for the low pass filter, and this we can design, we can choose. It can be 5 kilohertz, it can be 50 kilohertz depending on our requirement. So, this is the case of low pass filter. This is the practical filter, this is practical case. Practical filter. Then we go for high pass filter. High pass filter. The ideal case is here. This is pass band and this is stop band. This is gain, and here this is of course frequency. So, this is the ideal filter where the attenuation in the stop band is infinity, and from this frequency, which is the lowest frequency from where the pass band starts, the attenuation is 0. But this 0 and infinity, again these are ideal, and this sharp boundary between stop band and pass band, this is also only ideal. In the practical case, this circuit, this response for the actual filter will be like this. This is gain, and this gain is 3 dB and this frequency will be FL, same, this is frequency. So, this is the response of the high pass filter, this is the practical. And we will arrive at an expression for this FL, that is the lowest frequency, and this we can choose, as I said, depending on the circuit components. Now, the active filters, as I said, will make use of op amps, capacitors and resistors, just few capacitors and resistors, and filter design will be complete. The inductors are not used. There are reasons, and these reasons are: inductors are bulky and heavy and they are not integrable, and hence inductors are not used with active filters. So, this is the case of high pass filter, and then we can have the band pass filter. See, band pass filter. A band of frequencies is allowed. Before that it is not permitted, after that it is not permitted, and for the ideal this is the case. This is gain and this is pass band, this is stop band, this is also a stop band. But practically, and these are the frequencies FH1 and FH2, that means for these frequencies lying between the pass band, the attenuation will be very low, very heavy in the smaller frequency region and very heavy in the higher frequency region. And for the practical one, this plot is like that. And here this is 3 dB change again, 3 dB, and this is FH1, FH2 gain, and so this is the band pass. Band of frequencies will pass, rest will be stopped, and finally we have the last one, the band reject or band stop. This is ideally it is this. This is pass band, this is pass band, this is the stop band. This is gain, this is frequency, and this is that, and practically this will be like this, where this is gain, this is frequency, and these are those two frequencies L1, F, L2. So, this band will not be permitted to go in the circuit for further processing. So, now we will go one by one about these in details, the circuits and their analysis.